impact applications. Harsh has previously worked with Dhananjay Gadre at his lab and converged multiple projects, including one of the most cited course on NPTEL in embedded system design, an American Journal of Physics paper on science on stick apparatus, and helped spark tinkering in thousands of young kids from all over India at multiple venues. So that's the stage is yours.
Thank you, Sumit. Is this working? Can you?
Can you hear me? Yeah, hear him? No, it's not working.
Okay. Thank you for the introduction. Hi everyone. My name is Harsh, and I'm currently a PhD candidate at Washington State University. As Sumit just gave a very kind introduction about what I do and what have been my previous experiences. Today, I would like to take this stage to talk about this very cool idea, sounds like accelerating the future of electronics and beyond. And first, because I knew that most of the students who are listening here and online are BTech students who are probably graduating anytime soon, maybe going for jobs, or maybe have an interest in research in general. So I wanted to also give a little bit brief about what has been my previous experiences and my limited understanding of how things might work. So before that, I would like to lay down an agenda for this presentation. So first of all, which is a point being a bug for research, where I'll go about what kind of insect, if I may say so, you would want to be. Will it be a spider or a honeybee? We'll talk about it. Then the next point is where we come in as this idea of architecture 2.0, where now we are looking at an openness within the academia and industry, and there's a need of collaboration that we're talking about. I will talk a little bit about my previous experiences in sort of related work to where I stand right now in my research and work on AI chips and data-driven design currently. Talking about a little more technical details, what kind of work I work on, which is network or interposer design, and how maybe you can step into a new field, and how EDA, the design automation, which is probably correct for this department, the computer science and automation, the design automation kind of sits within the name. So talk about that idea and finally conclude if you have any questions. So first in 2024, this was a very interesting point which was pointed by one of my colleagues. I wasn't aware, it's a very common idea though, that do you want to be a honeybee or a spider? So if you think a little philosophically, a spider is someone who basically has a fixed sensor or a trap where basically there's a self-contained approach. The idea is that you have some notions, preconceived notions before, and you basically take any of the actions based on how far your web is, how far your reach is. Other option is being a honeybee, as you can see here, image generated by ChatGPT 4, where you're a honeybee who basically goes on different flowers, come back to a hub, which is the honeycomb, and produces the output, which is in form of honey. So do you want to be a spider or a honeybee? So when I first heard about it, it was okay, yeah, honeybee sounds cool. You have a lot of collaborations, you have different experiences. Whereas there is another thought, if you're going to be a spider, where you would have a very fixed ideas, fixed thought processes, and you go about things. They could also be in general around should we go for a job or should we go in research, having very fixed ideas. Is it how it works? Maybe not, in my opinion. So there are two ways. One is obviously having one single input, where you can see you're basically listening to one single compass. He could be a mentor, a professor, or you have multiple people doing multiple different things. Also here, one point of influence could be YouTube, who you're watching online, and who becomes the main source of motivation that if you should go for jobs or you should go within research. So is it, if you have multiple inputs, that's going to average out the outcome? Would you have a lower quality decision? I think maybe that is not true, because if you hear from different ideas, if you do different things in life, you never know how things might change. where as if I stand here giving a talk about a technical research idea. 5 years ago, I wasn't sure if I will do a PhD. So that ended up being my luck, where my current advisor accepted, and also my previous experiences put me in the right place at the right time. I'll talk a little bit more about it in the other slides. Before that, I would like to give a little bit insight on Architecture 2.0, where now we are exacerbated by the difference and overwhelmed by how high the hardware flops have been growing, whereas the interconnect bandwidth have been slower, where we are between a compute and a bandwidth gap, where we are looking for scalable research paradigms, where we are trying to look for how we can improve the algorithms, how we can basically have better compute system. Even the workshop name, if you look at the emerging computing systems, we are exploring these ideas. How can we bridge that gap between how fast the processor can compute something and how fast can we communicate the data? So we have, this comes under SIGARCH, which is one of the leading computer architecture symposium, where they talk about there's a current need of algorithm data set infrastructure, there's best practices, how we go into making it more open and including more people to do research. So the problem comes within, where are there enough people, or how many people do you need to do research to make sure that this field pushes in the same way which is happening with computer sciences, where you get a new algorithm or a new model almost every month now, and the newer architecture, the emerging technology have not been able to keep pace with it. So this is by one of the professor who is kind of leading the effort, Vijay Janappa Reddy at Harvard, where they talk about within the design pipeline of a chip. If you look at what are the volumes that we are considering, we have design cost, which includes the entire pipeline of designing a chip, which becomes a major contributor to the total cost. So hence the design automation, can you somehow reduce the amount of human involvement into the loop so that the SoC cost, the system on chip, the designing cost of the chip actually goes down. As we go towards a high volume commercial product, it becomes a minor cost, but still there are things which are to be met, which are like the scheduling, which are critical throughout the board, and we need a performance, we need a limited performance that has to be maintained over our power within the time and constraints that we have within the chip, which becomes another field like static timing analysis. So before going into how I ended up in like this field and why you should care about working in ML computing systems, because IISc is probably the best place you can be. We'll look into it. Before that, I'll like to give a little bit of preamble where a lot of things failed for me personally, and the field changed entirely, which I never expected, but it changed for good. So one first example was because just before taking my flight here, my mom was having a blood test. So we've had this issue, her veins don't show up. So there was some non-invasive way, can you make like a vein finder where you can basically have like an array of these near infrared LEDs, and the deoxygenated blood will show the vein where you have to cannulate. So I first tried prototyping this vein finder. It was in 2019. Went to a lot of hospitals around in Delhi. Turns out they use a rubber band which they just stuck on, and they just use their hand, and you're like, we don't really need that prototype. Fast forward a few years, I later realized that there was a paper by IIIT Delhi, one of the professors, Sujoy Dev, who was also advised by my current advisor. So that was interesting, where I could have taken a little more depth if I would have been aware or maybe contacted the professor in the first place that, you know what, this is something I'm trying. I've made it in like 100 rupees, and this could be something, but it didn't work out. The next thing that we worked on, which was also like a BTech project, I guess a lot of people have here, which was a low power LoRa based, which is a communication protocol to do some kind of a water pollution monitoring. Just another project that you might hear about almost by any of your classmates. So we tried around in Yamuna. The basic idea was, can you have repeaters for some kind of autonomous water pollution monitoring system, which looks like this. We made a PCB, we used a LoRa, which is like a fancier technology. If you have a line of sight, you can do a lot of communication. So, which was mostly in the embedded domain. So the next thing was donate smartphone.in, which I will talk about in a few later slides. And final was this NPTEL course with my mentor, or the guy I worked for 4 years before I joined my PhD program. So I had a plethora of experiences around embedded system design and a lot of varying things where I think that internally I was more like a honeybee, even though I had the thought of a spider, where a lot of you might agree that you do algo DS, and that's the one way to get into jobs. If you want to get into any other place, you want to do lead code, there might be a little more variance that you might want to give yourself, where you can try different projects, and you might realize the benefits that you get, or the clarity for what you want to do essentially comes back. So you can connect the dots backward in a way that now I think that it makes much more sense that why I had so much variance. It now gives me a different perspective in what I do currently, which we'll talk about. So there was this one board which was pretty cool. I'll give you a interesting insight. So this, you must have seen, a lot of people might be aware, Arduino Nano, which is a very standard 200, 260 rupee with a cable that you use. So this was designed at Gadre's lab, the CEDT lab at my undergrad institute, NSIT. I don't know if you're aware, Nicholas. So here the basic idea was that you have to always program an Arduino Nano with a cable, and you use Arduino ID to press it, because there's a compiler driven design. Is there any way you put a firmware and have another connect so that you don't need the laptop anymore, and you can do some physical computing, like scientific computing experiments I talk about? So this was what we at our lab kind of coded, where was this library called FiSync Fermata, where the idea was you don't need your laptop anymore if you have a phone and you have a right connection on this board with probably a keyboard, because you want a keyboard to type your commands like this. You don't want to use your digital Instagram way of doing it. So turns out it worked very well, because now it was an interpreter based. You don't need the Arduino ID anymore. You can directly write in Python. And this will do something as basic as a hello world for embedded system, which is like blinking a LED or taking input from sensors. So there was one experiment that we had right here, which is like, if you see, it's called thermistor, which is just a resistor which changes its resistance based on what is the temperature. So if I ask you, does hot water freezes faster than the cold water? So that experiment you can actually do. We did do that. It's called Mpemba effect, where hot water actually freezes faster than the cold water using this thermistor. So we in-house designed this board, and it became a cool moment for me. It was 2020. I was 21 years old, where one of my friend calls, oh, you want to come play cricket or something? I was like, no, bro, I have to take a class. So the way it turned out was, for a 21-year-old, it became a cool moment that, oh, I made a board, I worked on this project, and now because of the lab I was in, we were teaching this course in DU, one of the college called KMC, for physics honors, about 80, 90 people. I was single-handedly teaching Python and scientific computing. So that became another point where I was lucky enough to be in a right place, which was a lab environment. Because if I would have been like a spider, where, okay, this is the only path, which is lead code, not looking into research in general and finding what I actually love, so that might not have happened. So anyone else could have easily done it. It was just that I was lucky enough to be there. There was another project which later went into this inexpensive setup, which all of you here must have heard about Faraday's law and Lenz's law, based on what magnet you drop. If it crosses a copper coil, you have a rate of change of flux and voltage is generated. The same setup, if you just take it out with Arduino Nano, we made a different PCB for doing a research project, which again stemmed out of it, and we published it in American Journal of Physics. After I started my PhD, it got accepted. So there were two reed switch, which are just two plates. As soon as a magnet passes, it connects. So there's a conductance path, so you can read that signal. Essentially, very simple idea, not something, but one thing stemmed after the other. There was like series of events happening just because I was interested to do something within embedded systems, and I've heard about this professor doing a lot of cool things, and I was just there at the right time. So it's always important to be, open, be like a honeybee in a way that you're open to new ideas, having low inertia, where you can probably involve yourself and get your hands dirty doing things. Now, when the magnet passes through this coil, there's a rate of change of flux. Now, if you keep this coil a little too down, the voltage that is generated is going to be way more than what this ADC can handle. So we had like a op-amp to basically limit the amount of voltage that is generated, and then we again shoot it up in software. So that was one. Another thing that later happened because of all this exposure. Yes, please. Yeah.
I don't understand why, like, what's the point of the experiment?
So this is more like if you remember when we were like in high school, we had a pendulum experiment where you would have a pendulum, you have to calculate the time period of a pendulum. So this setup is essentially for someone who is hearing about Lenz's law or Faraday's law for the first time, not just on the paper, they want to actually experiment it. So the way it used to do, if you drop a magnet based on what polarity, you'll have a wave going up, the voltage will be positive or negative. Then if there's Lenz's law, then you can actually backtrack based on what is the speed, because you can get what was the signal, you can basically estimate what is the speed of the magnet. You can also get what is the dipole moment, and using that you can backtrack what might have been the magnetic uh, like in Teslas, how much is the magnetic capacity for the magnet, how strong the magnet is essentially. So a lot of experiments being done. We have this open sourced like a design. If you want to do it at your home, you can essentially just go on the paper and download from GitHub. Everything's available. So this exposure of doing random things, which we call as tinkering, because India has a culture of uh, DIY, which essentially becomes don't do it yourself, because you have everyone available at your disposal to just wash your car, to do everything. I started my PhD outside where I wash my dishes after every meal and make food, and now I'm a expert chef. So because having this DIY culture and being exposed to this tinkering, I also had the luck to be around in like Srinagar, where I saw we had multiple workshops spanning from very simple experiment where you have this copper coil and you move the magnet within, which basically due to the flux you have a LED glowing. So we had multiple such experiments within Sadbhavna Kit. So this was one thing I was directly involved in, and had the luck to be around in a lab where I can see multiple things. Now during COVID, when I used to go on regular walks, there were few things I tried around that, oh, if I expose someone to origami, like young kids, you can see they were just on the side of the road, like, oh, you want to try making a paper airplane, let's do a competition. I made that video, I tried doing random things. So the idea was, if we have an old used phone, can we essentially just donate it, and whoever needs it can probably use it to do kind of a very simple idea, anyone can just come up, it's nothing special. However, it failed miserably because even after donating the phone and everything, it turned out they were in such a dire need of money, especially around where I live in Delhi. They just sold a phone. So that was the first phone I was able to donate, like around 40 some phones, but still it kind of failed. And then I started my PhD later. But this experience now comes back when I think about the same problem in 2023. Now I have a small exercise for you. If you think about, let me give a little preamble. So there's this one guy, I don't know, you must have heard about if you follow a little bit of startup and similar ideas, Naval Ravikant, which is, I see some nods. So, which is a guy who is actively involved in basically making this culture open source and everything. He's an Indian origin guy. He talks about this idea that if I have a superpower to spawn laptops in random locations in the world, you're going to have the growth of humankind will be accelerated. That's what he says. So I was just curious, looking as a researcher point. Earlier, whatever I was doing was more like a student, where I didn't have a guidance. I had just some awareness. After starting my PhD and being under a mentor, where I have had the experience and luck to be exposed to people like, say, Sumit and a lot of great people, uh, having more direction. If we think about the same problem, if I tomorrow just expose entire education, say from class 6 to class 12, and there's like a AI agent who is going to teach you. So what is the influence that it thinks? So this is, I just gave this graph as an input. This is just an exercise I did for this workshop, where I was taking just to know a bias where Professor Vinod was talking about. This is one of the active part of research. I want to expose you guys literally to what might be something that can actually go wrong, or the point of research that we need to work on. So if you think about this same graph node, there are some nodes which are communicating to each other, which are probably children. So the way it is set is their mothers, their father, and there are some kids based on how many kids they have in the family. The kids meet in school. If there's any bad habit or some fake news that is infected, how fast will the entire graph structure, like how fast a society or the smaller community will start accepting that. So I'm not giving any inputs here. It was being predicted by GPT-4 that what does it think, what will be the influence. So GPT-4 kind of thinks that US as a country will be actually better off than India, which is kind of, I'm not sure, maybe in the next slide we'll go into like why does it think so, that basically it thinks that there'll be a difference in how information or fake news is spread in India versus US due to influence which is at home. So the here I'm not giving the input, I'm just giving the structure. Again, I'm reiterating. And this judgment is coming from a AI model, essentially, that what does it think for this input graph structure? Do you think the fake news is going to spread? How would it vary based on the country difference? So what does the thought about the country in that regards? So it thinks that the negative influence will spread more often in a Indian setting. So if you look at what are the reasons, what reason is there that it thinks that there's probably going to be that kind of difference is because it thinks that in India people are generally motivated towards material success and wealth, whereas in US there's an entertainment culture and social media. Do you really think that is true? I don't think so. This is wholly wrong, and this is where AI governance and the ideas of hallucination comes in. And you will also realize later, I'll talk about how our field ML computing system has a direct impact on how these future models are going to probably take decisions or make policies. So in India, like scenario, they kind of think that the current population follow a path of lower paying outcomes because we are mostly just motivated for money according to the model, which is wrong. And things that in US we have percentage of curious individuals more often, maybe because they do more random things. I don't know. I don't have the reason, but this is what GPT-4 thinks currently. And this has a direct correlation when you think about some of the later slides I'll explain. So if you look at one of the prompt, which was like the bucket prompt, I gave the umbrella statement, which was what does it think that what is the percentage of kids that are going to fail in life, essentially. Very broad question. It has this expectation that in India, okay, 10%, whatever I kind of normalize around bar and ChatGPT. It thinks in Afghanistan and Nigeria, the percentage is going to be higher, which is the probable AI bias, which you see almost everywhere on Twitter talked about what is happening within the field. Now, if you have any emerging computing system based on, because if you look at cross attention is what has the positional encodings, it's in the end is multiply and accumulate happening over different lengths. So if you have some approximate computation happening, that can actually be regarded to changing how the next word in the sequence is going to be, which one is giving more probabilities, and that would be selected. So when you complete the sentence, you might realize that what ML computing system, how approximate it is, or how correctly it defines is going to impact what will be the output accuracy or the correctness or the bias that it's going to have. So that is one active part of research where you have a direct impactful, yes, please.
So is it like that LLMs have this bias because of the data that's being trained on? Because I have heard like ChatGPT and like Bard, they have been trained on the data that's more Western influence.
Yeah, I was coming to that. So it is going to be that way because we don't have in our regional languages. There was a interesting. So if you are interested in this line of research, there's like a plethora of work done by one of the guy at IIT Delhi called Mossam. He just released a paper called JE Bench. So the idea is they gave JE questions to all these AI models, had human interpreters based on what was the ranking in 2023, and they compared. So there are people doing work around looking at how you can make it more inclusive and bias. There's work in IBM research. I know a couple of people working with Kush Varshne from MIT. They're working on something similar. So the basic point was being just something which is highly impactful currently is also going to have a big impact based on these ML computing systems, because at the end of the day, your computational prowess in a sense that is it approximate or what layers are you mapping and which parts are being approximated is going to have an impact on what will be the final output. So before going into like the depth of my research, I wanted to also give a little bit sense, just comparing based on CS ranking, where say in the field of design automation, which I mostly do my research in, I wanted to look at, okay, how does the scope for say US looks like currently, where research paper is the currency and their top conference considered. Now in CS ranking, one limitation is only ICCAD and DAC are the ones which are selected. Sumit was mentioning maybe I can open source my part of code, which I can probably do because I consider date ICCAD. I just had like a scraping being done through DBLP to make it more inclusive to journal papers as well. So you can see California being California with all the big universities has a score of 71. This score you can just see as bigger the better. We have different universities. You can see some place like MIT has like 3.5 and there are multiple places with zero. Like Oregon has Oregon State University. Turns out in EDA they don't have a lot of impact coming in. WSU, which is not very highly ranked, the university I come from, for the entire computer science, I think it's 76 world ranking, but takes a big rank, like I think 14 or 15 when we look at EDU, my lab being top. I was comparing with India, where one of the professor clearly stands out, Professor Mukhopadhyay, and we have IIT Bombay, we have IISc, we have Goa, we have Delhi for a score of 2 within EDA. So the question might be, do you need hundreds of professors and hundreds of people actually actively working on a part of research? Maybe not, because if you look at just this one score, which is so high, even higher than MIT, if you look at it's 5.8, is coming from just one lab. So looking at the research, if you have a very niche field, because that is what the idea becomes, you work on a very specific domain, you can actually have a very big impact, which is going to bring things on a global scale. You can go on CS ranking yourself and compare. Yes, I see a question.
What's the last name?
I think Professor Devi Mukhopadhyay, I can connect with you and maybe IIT Kharagpur. Yes. So they work in EDA. They have here in IISc, Sumit is one person who works. He has 5 papers which shoots up the rank for EDA. But if you look at systems in general, which includes all of these fields, again for US, you see it kind of getting normalized. A lot of big players, even professors here, Professor Vasu from Wisconsin Madison having Wisconsin as a score, UIUC, a lot of big places, University of Michigan, UPenn, Penn State, California again, California, UT Austin, State of Washington. They have like a score being given here, Colorado State and Colorado School of Mines being one of the places. But if you look at in India, we have a lot of comparable places where again, IIT Bombay, I think one of the speaker here, Professor Panda, is one of the reasons for the score. Again, looking at Delhi has a very high score and IISc again taking 2.1. IIT Goa, BITS Goa being another example, BITS Pilani, IIT Kanpur. So if you look at the systems, the exposure within the country, there's a big places where and multiple places where you can actually get your hands dirty and get into the field in general, where these are all the included fields and there's a lot of cutting edge work happening. So again, after the architecture 2.0 workshop, where a lot of professors and industry leaders kind of came together in around September, they were talking and having the main focus around ML algorithms, data set, how do you make these tools and infrastructure, which comes under how do you design better AI chips, or how do you make these servers communicate better with each other, or how do you basically do a ranking algorithm within so that the threads could be run parallelly if in a requirement is being researched. How you can do a better workforce training, there are industry relations. So there's a lot of great places where you can work at essentially. Now I would like to talk a little bit about in specifics of my research, which is data-driven design and optimization for a specific thing called chiplet-based system. So before that, I'll explain everything. After this talk, you'll have a good understanding of what my research kind of encompasses and have like a high-level idea. So we know industry is going towards smaller nodes. You must be hearing from 32 nanometer to even smaller. Now we're at 3 nanometer. But when we go towards smaller nodes, the yield is decreasing. Manufacturing of a larger die is not economical anymore. You can see here as an example, this was one of the wafer kind of simulation on gamma distribution I coded. I have it on my website, where you can see a 10 millimeter square die on a 3-inch wafer just has 32% yield, which is going to mean that only 1 out of 3 chips are going to be working completely. There has been some ideas explored around 3D stacking, because at the end of the day, you have like a given fixed area overhead, and you want to basically pack as much as compute possibly, or as much as data to be made. You make like 3D stacking. However, there are issues like temperature hotspots, because they're going to be like, if there all of these cores are running, you would have some power consumption within, and that would mean there's going to be hotspots created if there's not a well considered packaging environment. And we have additional dollar costs due to these keep out regions where you see each of the router. You can't actually place any of the compute over there. So these are some of the reports where there was this new idea that, hey, what if we take a monolithic chip, we take a bigger chip, and we know that there's going to be 10 defects. What if we break it into like 16 parts? So chiplet is basically a smaller die where you're going to now fabricate on a single wafer. You can see here as an example, all of these white boxes essentially become a chiplet, which is like a smaller separate computing core. Now that if it was a single one, you broke it in 9 pieces and then you connect it. Now that you're connecting them through a network on interposer called as NOI, again, network on interposer, you're trying to basically amortize the losses that would have happened. If there was a defect here, earlier you would have to throw the entire chip, but now maybe just one chiplet would be thrown. So you get an economical manufacturing method. You can do binning, so your yield improves. And there are models which tells how much there are improvements. But there is, when you do something, you open another Pandora's box. Here, the unsolved challenge becomes the scalable communication, because now these chiplets are physically far apart. So that would mean that the communication cost is something now you have to pay for. And still you would have thermal issues, because now you're coupling through some kind of bumps, which are more like solder points, so you're going to have, and then defects can still occur on the chip. So we must kind of think about how industry, if given the problem, is thinking about this paradigm shift. And for industry, the biggest motivators are they want performance and also the fabrication cost. So for ensuring the performance, you want to target communication, because now we saw things became physically far apart. So now you want them to communicate better, or somehow you want to improve the overhead that you have in communication to reduce. So system scalability and fabrication cost is hindering why people are not doing it yet. Actually, AMD has already started chiplet-based designs, and NVIDIA is exploring dialects, which are a little bigger chips. So we have a poor technology scaling of the wires, the larger physical distance that we saw, and we are in a power constrained environment because we are already in that constraint. However, efficient NOI can solve this problem, but we obviously want the two things, that performance should not be compromised, and we also want energy savings, because as the system size scales, how much energy your system is taking, we are going towards energy efficient paradigms. This NOI, which is the network on interposer, because you can see how big interposer is. Each of these darker square cores that you see are chiplets, and the pink links kind of show what is the network on interposer, which is like the interconnect fabric. So we are looking at NOI because it's the biggest area, it has the highest area, and the energy consumption becomes the bottleneck for such a system. So there is an immediate need entirely for these cable architectures. So there's been some related work around in the last few years, 2 or 3 years, where intact, one of the paper by a very famous author called Pascal Vivek, they had a paper called intact where they demonstrated that we have low latency interconnects that we can ensure the communication to be low latency. Another was a joint work by NVIDIA and Stanford, Professor Shao et al. In 2019 called Sigma, which was for deep learning applications. Say, for example, you want to run CNNs or you have other models. So how will you do tiling optimization? How will you basically map that system onto this chip to run? Next work was by a famous professor, I really like his work, Tushar Krishna, where they had a work called Kite, which is primarily a torus-based architecture, and they included a new idea of kind of a old wine in a new bottle, because it was already implemented way before, but they introduced a torus-based architecture with some kind of misaligned routers in between. The next was work at Wisconsin, Madison, and Arizona, SIAM, which Sumit has been involved, where They had a 2D mesh topology, and they had an evaluation framework for a 2.5D system. But none of them were DL workload aware, where now that we're looking for AI chips, is there any specifics that we can have, how we can make chips the ones which can efficiently run any of our machine learning workloads. So next came SWAP, which was there to fill that gap, which was application specific CNN accelerator, where they had some awareness on the fabric based on how the cores will communicate, which was in 2022. But again, if you're looking at a server scale environment or a data center, there are multiple users which are requesting multiple machine learning workloads. So there is a need of concurrent CNN tasks, which Floret, which is one of the paper I talk about, my paper from last year, kind of filled that gap. So we considered a workload-aware NOI architecture for specifically a data center scale, where you would expect multiple users inferencing from the chip, and they would be like up to 8.8 billion parameters is what we consider. We had a beautiful design. It's called a space filling curve. You would see the fractal kind of designs that we have. We have a SFC-based architecture. We enhanced performance gain, and we also had lower energy consumption. We'll talk about and we'll see visually why it performs better. So that'll give you a little more insight. We had like a hardware software co-design approach, where we were also looking at how the hardware should be and what should be the software that actually maps onto the system. And in the end, it makes it a little better for our industry because it has lower fabrication cost, which was like a critical step towards better chiplet-based many core system designs within my field. So let's talk about the SFC idea. Before that, I would like to point a little bit of a thematic similarity, a structural similarity to a human brain. Now we have different parts within the brain where some of them are, like for example, occipital lobe is for depth estimation. We have the frontal lobe, which has series of tasks when I'm doing any kind of thinking process. So there are multiple tasks which have serial execution within. And then we have concurrent education for execution, where we have some tasks which are running parallel to each other, depending on what type of task we are doing. So space filling curve essentially is like a 1D line, which is basically bent into a higher dimension, could be 2, 3, where you have like a algorithmic mapping technique. How will you connect some of the points in like a 2D space, where you use this kind of space filling structure for preserving locality. It'll become a little more clear what it means by locality preserving, or basically you're able to ensure the place where you start, you want to come back there, like a ring. So we'll go over that idea. So SFC traverses the entire 2D or a 3D area with no closed loops, which is like a artistic design. You might have seen some designs within India. We have kind of the structures similar to SFC. So it becomes like a neuromorphic architecture where we kind of mimic the brain. When we were working on this paper, we weren't aware we have this kind of similarity. It later came as a revelation that we have different parts which are running parallelly, and there is a serial continuum within the structure. So we have like the possibilities of running things parallelly. At the same time, those things within can do serial execution. So we'll talk about the merits and how it looks. So first we look at the physical realization of the SFC structure. You can see this floret. So broccoli is like a floret where you have different flower, and then you have multiple different flowers. You have different petals, as you can see here, a red one, a blue, green, yellow, and purple. Then we have a hierarchical top level network which can communicate with it. And then each of these petals are separately woven out using a single connection, which is a SFC. Now, some of you, if you have a little bit of background with computer science, you might realize that it could be essentially a traveling salesman problem. However, how hard it might be to iteratively solve it, and it's not the most optimal way of solving the problem if you do it iteratively. But this becomes a traveling salesman problem where you essentially start at one of the nodes, you continue going green, yellow, purple, and then you come back to where you started. So there's a benefit that comes out if you look at CNNs, which are convolutional neural networks, which are done on the data center scale, especially in Google, where if you have dense nets and different res nets for doing image segmentation, we'll look at how it works. So within CNNs, we have this idea where activations, which are the packets, if we are thinking as a systems person, will move from Li to Li plus 1. And there's a need of contiguity. You don't want any break within the system. You want to connect all the nodes in the square, or it could have been different dimension structure, but you want to continue going so that you start where you were. You don't want to leave any of the resource, because each point here is like a resource. So you want to continuously go and reach back where you started. So NOI design considers head and tail pairs, which are like location. You can see it's like a central location. Now there might be a question: how many petals, how many SFCs do you need, and how large or how long they should be. So there's a trade-off between how long and what will be the number of such SFC or the petals in our structure. So there was this consideration that we did for the CNNs, that if we have multiple different CNNs, how would we determine the number of these petals and how long they should be? We have limited number of, say, the fixed number of cores or the chiplets that we are connecting, if they're 64, if they're 100. So we looked at the average hop count, which will come. But before that, I want to point out the common property of CNN, depending on whichever it is. We have convolution layers, pooling layers, then again we have convolution. It keeps getting smaller and longer when we look at the final vector length if you implement the CNN. So we have this nature of Li to Li plus 1. After each of the layer, the data essentially just goes to the next one. However, there might be some differences where we have ResNet, or this is an example of DenseNet, where we have connections from the first layer to the last layer. However, still the data is going to flow through L1, then L2, then L3, because L4 cannot start unless you have the activations from the previous layers. So you will finish, the data flow is going to be from Li to Li plus 1, essentially for CNN-based neural networks. And you can distribute based on what you might be running, like a transformer, which we'll talk about later. So I'll do a comparison of my previous paper in 2021 with Sumit Swap and this design called Florid. So in case of Swap, we had an application-specific design, but at runtime, who knows? There might be a new imaginary net coming in, which has different requirements. So what you optimize or what you thought the connection would be required, that we see that chiplet 9 communicates to 15, so let's have a longer communication, like a bypass through them. However, at runtime, at the real time, there was some other ResNet that came, which needed some other communication between some other chiplet. So because of that, there are unconnected islands that are created. In Florid, we continuously map. We start at H1, we keep mapping to T1, then we go to H2, we continue to T2, H3, T3. And if we need more resources, that is, we are out of the resource that we have available, we're going to come back at H1 where we map the first layer. So we always maintain that contiguity along this Hamiltonian or a continuous path meeting all the nodes within the system. Here, as you can see an example. So during the mapping, if we reach one of the tail, in case, say, the yellow one is already working, and we were at this position, so we could have jumped onto the purple path. So there could be a scheduler, even a controller that can take care of that. So we have multiple options. So we have an inherent redundancy within the system. What I mean, in case if something breaks within the system and yellow petal is not available anymore, your system is not going to be at a halt, because you have an inherent redundancy where you can just skip the yellow part and go directly to the purple. If you are coming from down from green area, if the yellow is broken, you can go to the purple. So you have this redundancy along the path. So that makes it useful for considering on this server scale environment, even if after you have some kind of redundancy within the system baked in. So we wanted to know how long the SFC is and how many of them you need. So we have this one celebrated factor, which is called average hop count, which is how many hops are you going to expect, how many paths of communication are you expecting between these nodes that the data will communicate. So you want to minimize this average hop count for all of the head-tail pair, which means that on average, if I'm doing any of the workload on this given system, be it this Florid kind of SFC structure, how many hops it is taking for communicating. Say first has to communicate to ninth. It will take 10 hops or 12 hops, depending on how the path is, how it has to traverse. So we do this minimization, and when we look at the graph, we get like a trade-off of what are the number of SFC and what are the size of individual SFC, because there's a dependence on workload, what are you running. So we look at the average case where we get optimal number of SFCs. We also explore that if you have unequal length of SFC, because there could be a case where the yellow one is smaller, the blue one is bigger. If you have this kind of difference, we saw that on average for different workloads, which are a mix of these ResNets or VGG or DenseNet, we had all of the considered CNNs, which are different kinds of neural networks, which have like skip connection, which are connecting further layers. So we saw that consistently having equal number of SFCs or equal length of SFCs made sense, because we had on average, this was like an empirical result showing what is the performance. Latency is how much time it took for doing the part of communication. So this became like a basis in flow rate for all of the system size, which is like a balance that we consider. So by doing that, this is one of the parameters I can give you a little small brief about. We talked about routers. So routers have individual ports. Now each of these ports are essentially telling you how many other chiplets or other nodes you're connected to. So because in case of flow rate, you're just connected to one who is ahead of you and one behind. So you're not connected to any of the other flarings, which was in case of mesh, where you're connected in X, Y, left, right, up, down kind of thing. Here you're just connected to a predecessor and the successor. So you have consistently smaller number of routers. So the peak of the router port configuration, that how many routers are there with 1, port 2, port 3, and so on. We see across all system sizes starting from 36 to 100 chiplet system, we have consistently smaller routers, where we can see we just have mostly 2. And if we are in the top level hierarchical network, we might have 3. So not just that, we also have reduced number of links, and the length of each of the link was also smaller, where you saw that there was like bypass links. So bypass are longer, so you need to have like a repeater structure, and it takes longer number of cycles. In case of flow rate, the design itself had some kind of this nature where, because you're just connected to the next one and you're minimizing the average hop count, we had all of the links have single hop. In case of swap, there could be bypass, as I was showing you previously, that there were longer range communication, or in kite, we have like a bypass link. Here we are able to keep all of the links as single hop. So that was one of the other advantage. We'll see how it makes sense, but look at the fabrication cost, because if you look at the network on interposer, which was the 80% of the area, we already have reduced the number of routers and links, because that is essentially what the fabrication cost of the NOI depends on. So we have the inter SFC, which was the hierarchical top level network, the one in black, and we had an intra SFC part, where you can see we have the area which is going to be, because it depends on what is the router area and the links. You saw the links were smaller, and you saw the number of routers were smaller consistently when compared to other architectures. So we had like a principal difference in fabrication comes down to like the relative NOI areas between both of the architecture we are comparing. So we had like 80%, 61%, 49% with respect to kite, SIAM, and swap, which are some of the current state of the art within the field for a 36 chiplet system. If you go on a even bigger system, it's going to cross it. I think it goes about 1.9 times, as I remember, for SIAM. For kite, it's a little higher. So as system size scale improvement increases, because as you're going bigger, you have more smaller links, more of the routers are smaller. So you have that consistently. So let's look at where these concurrent tasks, as we said, it's on servers. So we have these real-time video analytics, which are very well celebrated ideas. One of the bigger is in cloud computing, where multiple CNNs can be used to improve the performance. There are multiple users querying on the server for multiple different tasks. There are ResNets, there are VGGs, which are used on especially Google Cloud if you use Google Colab. We have edge computing, where you might have one usage where multiple CNNs can be used to process data locally, and we can have some kind of a federated ideas explode around that. So our data set that we considered, we had something like a ResNet 18 on a CFAR 100. I don't know if you guys are aware, CFAR 100 is one of the data set where you have 100 types of images. So one of the classes, we start from ResNet, we have VGGs and DenseNet, which was like the all-to-all kind of network connection that we have. And we go up till ImageNet, which is a bigger data set. We go up till DenseNet 169, which is famously used in Google's photo tagging feature that we have in your Google Photos. So it has 890 million parameters. So the workloads that we considered were like a list or a stream of CNN tasks, which had multiple different neural networks running parallelly, which are being given to the system. And we did like a comparative study looking at how much is the execution time, what is the power consumption, and hence the energy that the system is taking, and so on and so forth. So we had total number of parameters starting around weighing around 100 million to we went up till 8.8 billion parameters, where we had more of those ResNet because it has 900 million parameters. So we went up to 8.8 billion parameters, where you can see the example. Example is there are 5 ResNet without VGG and DenseNet that the system is required to run. And we had NOI frequency, and these are some of the GRS parameters that are standard within the industry. We don't need to worry much about it. So let's look at the activation flow. I have kind of discussed about this idea before. I just reiterate that if we start mapping one of the CNN here, we continue mapping. If the requirement is so big that we have like a dense net where the number of chiplets that are required is, say, for example, 120, and we just have 100 chiplets, we end up at the same place where we started. So you don't have to do any of the further communications. You're able to minimize the hops that you have within the communication, and that takes care of it. So I have this small slide which will show you some of the difference between SIAM 2D mesh, which is the standard which is used, the most basic interconnection fabric, and we have flow rate where you can see the structure. This shows power consumption as the time of execution. You can see consistently flow rate for workload 7, which was the biggest. It is able to do with less power. And you'll see by the time it will finish, it has already finished running the workload. It has already executed. The SIAM is still executing the same workload. We have 1.8 times latency improvement, and the energy consumption was way lesser that we can look at. Here, some of the slides will show. So let's talk about the performance, where we have average improvement of 27% with respect to Kite, which is the blue bar. The grayer bar is SIAM, which was principally a 2D mesh. SWAP was the application-specific architecture, kind of having issue of being optimized at design time, but on runtime something else came. You were not prepared for that. So SWAP has a little higher, as you can see. And flow rate has a consistent performance improvement, where on 100 chiplet system, you can see there's a 100% improvement, 105%. And as we go on a bigger system size, you can see the peak is 1.5, 1.6, 2.1, 2.4. So we are seeing due to this data flow aware nature, because we were aware that the data flow has to flow from Li to Li plus 1. So you can have like a flower kind of structure where you go over all of these petals individually and start back where you were. So that is basically the key idea, the key takeaway, if you have to take one thing, is having that data flow awareness within the structure that help having more of the performance improvement. In case of skip connections, because the order of which the skip connection exists in these neural networks is limited. So 90% of, if I give you an example, in case of ResNet 34, I remember for CFAR 100, about 3 times of the traffic is just Li to Li plus 1. So that also flows through the NOI here, and we have considered that where we show consistent improvement. In case of energy savings, we can see average improvement is up to 2.7 times. And with respect to SWAP, which was the design time optimized of my previous paper, we have 1.6x. So smaller router ports with reduced number of links led to the energy saving. So if you look at fabrication cost, here I have a little more animated kind of a structure which shows you 4 things. So energy consumption on the x-axis, the latency, which is basically a measure of performance here, what will be the time of execution. The size of the points tell you the fabrication cost, and the color of the points tell you about the carbon footprint, because there are 2 aspects, capex and opex. When you look at the recurring cost, your energy consumption becomes the measure, and the infrastructure, the creation of the infra, the fabrication cost based on how many routers we have, how many links we have smaller. So you can see we have greener, smaller points, which are towards the utopia, because everyone wants to kind of come here towards the origin. So we are towards the origin when compared to all the other architecture which right now lie in the space. Here you can see very red kite, then you can see swap, which is kind of yellow because has lesser links, however, it doesn't perform that good at runtime. So we had this kind of a structure. There was a vision forward tab that we kind of talk about where the same structure, we can have heterogeneous system architectures where each petal could probably take care of one specific task, which it might be required for. There could be work in influence maximization. There is one of the places where it can work is in 3D because you can essentially, instead of a 2D structure, you can imagine this in 3D, where each of your flower can actually go downward, or you can have this top level network somewhere towards the center. So the key idea here was maintaining the contiguity, but now you can have different computational platforms, which could be accelerator, DRAM, CPU, GPU, which can take care of that. So heterogeneous integration could be done on this SFC structure, and it could also accelerate multimodal. Yes, please.
Could you please explain the first point again?
Oh, okay. So if you look at the number of links, if you have a mesh, so this was just the complexity, what space we are looking at. So in case of floret, let's do a thing. I hold this core, and maybe you can hold this one and I cut it. If we just straighten it out, it's like a linked list, right? You can see it's essentially just a single line. So if there are n people standing and all of them are holding hands, how many people? N minus 1. So you have, as the number of cores will increase, you will always have order n. Whereas if you look in a 2D structure for a mesh, because the number of links is higher, when you calculate, say, for a 36 chiplet system or a 36 core, how many links are there, it becomes twice of n into n minus 1. So there is that n square factor. So if there in future you have hundreds of processing elements and you're connecting, so you would basically scale better in order n. So that's the big picture idea I think you must have heard. So within transformer models, because in transformer that we're looking at these examples, ChatGPT or machine translation that I was talking about before, we have 4 major components: input embedding, KQV computations, core, and feed forward. So feed forward is essentially like one of the part which has static component, which could as a macro be done on a SFC based structure where you can have this Li to Li plus 1, which was other thing we explored. For this paper, I got a best paper award in the same conference. It was in transaction and embedded computing systems. Last year, the swap paper that I was talking about was another best paper that we got, which was with Sumit. So now we are looking at some vision forward around because the problem is not solved. There are thermal issues. When you're mapping so many things parallelly, if you're able to run so much parallelly, there's going to be a hit, which is because life is about trade-off. My advisor says that there's going to be trade-off always. So if you're running everything so fast, you're going to have much higher power consumption. And so the byproduct would be your thermal issues. But can you actually estimate at dynamic time how much would be the thermal impacts? So that is one other form of direction. Or there are stable diffusion ideas. Can you have a heterogeneous system for stable diffusion architectures to basically recreate these ChatGPT DALI images? So Floret is kind of that first workload-aware structure, which was for a data center scale. There were multiple benefits, which were high performance, lower energy consumption, lower fabrication cost, and lower carbon footprint, essentially coming due to having smaller routers, lesser number of links, smaller length of the links, and being data flow aware. So that was overall of what was my research ideas that have built in. And when I look back, kind of feel about being like a honeybee. One key takeaway I can tell you now that you're in kind of a position I was, I would say 4 years ago. I think you should kind of expose yourself to newer labs and also trying out things. It's like ML computing systems is a field where currently there's a big, very big void which could be filled up because a lot of you know about programming. You also learn a lot about how the current cutting edge is working, and there's a lab for emerging computing systems. So I think that could be like a good package for you. I think with that, I'll end my talk. If you have any questions, you can just ask me right now or later. Just get hold of me whenever. That's mostly it.
Let's have a big round of applause for that. Okay, time for question. And remember, you have to ask question. If you don't ask question, I will now point out and make you ask question, or I will ask you question. Don't look at your next person. Your next person is not going to help. Or maybe hers, you can check whether the audience understood your talk well or not.
No, I think they were well engaged. I
Okay,
could
you are
see all
not
of
giving
this.
them hard time. Come on. At least 3 questions I want from audience. Yes, please. Can you, what is your name?
Sorry, my name is Rajesh.
Rajesh, I'm with the MD. I was actually a student here way too long ago. So I want to discuss that. One other constraint that you could consider is I know you said it's all about trade-offs and you're looking at number. The other thing you might want to look at is the reliability aspect, because you said you're reducing the number of links at the list.
Yeah.
If you lose one of those links, you lose the
You
entire.
lose the entire pattern.
Yeah. I don't know if there's an answer, but maybe something.
Yeah, I think that's a point very well taken. In fact, I would say when we were having the review rounds, one of them said that if you look at the robustness, is what they used as a word for if, say, in your top level network, one of the links stops working. So one of the fabric consideration they said that was that within the top level network, because it's the highest priority, because it communicates to other petals, you can have more like a all-to-all based connections, because there you can ensure there'll be some loss, but ensuring all-to-all connection there. But because the top level network is always small, so when you scale onto bigger system sizes, you will have a smaller increase in fabrication cost. However, that'll take you a longer way. So again, the trade-off choice. Yeah. Thank you. Thank
Okay, anyone else? So you should also give hard time to the speakers. This isn't just CNN, silent audience, right? Anyone? Yes.
Hi, I'm Neetu. I'm from Cochin University. I'm a research scholar. So my doubt is the number of chips connected in a petal is fixed?
That can change. So if you consider CNNs, now you would also have to look at on the data center scale that we're talking about. It's going to be different. Say if it's going to be Facebook or Meta's data center versus Google, because they have different application characteristics that come in. So that length would be determined by what is the average requirement of one of the workload that is running. 3D, we realize our lab is working on 3D that we had different length of SFCs as well, depending on the applications.
So like every petal will have the same number?
We showed in the current consideration, the current constraints that we had, same number actually worked better. So one of the figure that I had, if I may go a little bit back, I can show you how this works. Yeah. So if you see this one, the heading says about the unequal SFC and the equal SFC. So you can see consistently, because latency, the performance is our first great citizen, right? So we have consistent performance improvement on our workload. There could be workload consideration where this might vary, but for CNN specifically, the domain of convolutional neural networks, we have consistent improvement if we have just same, because that makes sure that you have like a uniform, the load is well balanced if you have equal lengths of SSCs.
So this is meant for CNN instance?
Yes, this is for CNN. In training, you have backprop, so you might want to have bypass links. That is one thing. But for the problem that we consider, which is the data center scale, we are just looking at inference. If you want to do on the edge, there is work on training that shows otherwise. Okay, sure.
Okay, any more questions? Again, we have to ask questions. Otherwise, you'll sit here, Hers will be standing here, we'll be here on. I'll not move on. So, anyone? Yes.
So, hello, my name is Mayan. I'm a final year engineering student from Christ University. So my question was, you were talking a little bit about edge competition system within the node section. And the first priority we were talking about the reducing the latency of that thing. But don't you think so? Using the concept of edge competition, we will face the same thing again, issue of latency.
So the thing is, when you're looking at edge computation, you define a smaller space. So there is one concept of pruning the models. Here, these are all I would say commercial grade where you have much bigger parameters. You can have the exact same ResNet 34 that we were talking about in under a million parameters. So when you're on that kind of computation, the same exact constraints can work where you have a prune model. So on the edge also you can create. So I'll tell you a thing. First, I wanted to go on that table. It's a little later just to show you what I'm talking about. After this one, we have, yeah. So if you see neural network 1, ResNet 18, it need not be 1.8 million parameter. You can have a prune model too, which work fine if you compare to. So within the conference, there was one of the other best paper candidates who had a work where they were doing similar CNNs, but they had a MSP 432 system. So they can have multiple of MSP 432s in a flow rate structure that they are exploring right now to make sure that they can have like a ring or a petal kind of structure communicating, and each of them taking different tasks and having the activations flowing through. So then that communication could basically, that's a physical aspect of what they're doing. So they have prune models. So the same methodology is being applied for that.
Anyone else? Okay, if there is no other questions, I can have a big round of applause to her also. We have a small memento from CSA to give to us. Thank you, Mas. So next we'll be moving to the high tea. So maybe you people can slowly